session, I'll be talking about how do we really build an optimal portfolio using R. So here the expectation is you have a good understanding of the basic features and functions of R. So here our objective is to create a portfolio which can, let's say, minimize the risk. Right? I want to create a portfolio of, let's say, five different stocks. I want to find out in what proportion I have to invest in these five different stocks so that my overall risk is mitigated for a kind of a given amount of return that I am expecting. So it's more of a kind of security selection process. So what securities do I really need to invest in for what kind of return? And how much percentage do I need to really invest in each of the securities? So basically, it's a kind of an optimization problem. So there will be some kind of mathematical models that are involved in building these kind of optimization solutions. But we would be using the same using R. So there are a lot of built-in packages which can perform that kind of optimization for us. So all we need to be comfortable with is how to execute those kind of packages, and once R has executed on the data set, then how do we really interpret the output that is given by R. So this is what we are going to look at in this particular topic. Now moving forward, whenever we talk about a portfolio or optimization of the portfolio, we know that it is primarily based on the concept of correlation between the various products, and this correlation is going to reduce the risk. So depending on what kind of correlation exists between the different securities, we can reduce the risk. If the correlation is very high, probably the diversification will be a very difficult aspect. But the lesser is the correlation between the two securities, we can create a very less risky kind of a portfolio for a given amount of return. So just theoretically, if I have to showcase, let's say I have two securities, right? I have two securities A and B, and I have invested W1 in A and W2, which is 1 minus W1 weightage in B. So if I have to really talk about the variance between W1A and W2B, based on the concept of variance itself, it comes out as W1 squared, the variance of A, plus W2 squared, variance of B, plus 2W1 W2, the covariance that is existing between the returns of A and B. This is the typical formula that exists to compute the variance between the two securities, right? So the covariance in turn is based on correlation, because the covariance between A and B can be written as correlation between A and B multiplied by the standard deviation of A multiplied by the standard deviation of B. So the higher is the correlation, higher would be the variance of the portfolio and vice versa. So basically the variance can be very much reduced if the correlation is very much negative. And we know that the correlation lies between +1 and -1. So if the correlation is very close to -1, I can very well reduce the overall correlation and overall variance of the portfolio, and I can very well take it close to 0 as well. So but in reality, getting two securities with the correlation of -1 is a very difficult aspect. So this is where what is that particular proportion or what is that particular weightage which can reduce the overall variance of the portfolio is what that is very much to be understood. So this is where we will start first understanding quickly the conceptual aspect of it and then putting the same into the R model. So for this I would like to get started with the mean variance framework or the model, whatever you call, which is typically a Markowitz model. So here we are talking about different asset classes or different assets for that matter XI, which are nothing but different securities. So each security, the returns we are taking and we are calling them as XIs. And when I am talking about a portfolio, we are typically talking about different weightages in different securities. And the overall is summed up. So I am trying to invest different weights in different securities in such a way that all the weights sum up to 100% are 1. Now here this particular combination, I can talk of two ways. My combination could be either affine or even convex. Now when I am saying affine, regarding the weights W1, W2, W3, no other restrictions. I don't have any other restrictions in the affine case, but I may put some kind of extra restrictions saying that none of the weights can be negative. So let's say all the weights W1, W2, W3, they all needs to be positive. They can't be negative. But in the affine case, they can very well be negative also, which means we are talking about shorting those particular assets. Whereas here, we are talking of only long only positions, which means I cannot have negative values for the weights. And then when we are saying we are doing an optimization solution, we are trying to find those possible values of the weights so that the needs of our portfolio are typically met. Our objective of the portfolio is typically met. And generally, the different kinds of objectives people go with. Either they can say, I want a completely minimal risk portfolio. That particular portfolio which gives me the least possible risk. Right? That could be a kind of a requirement. And or sometimes people might look at the maximum returns. I don't bother about the risk, but I want the returns. I expect the returns to be the maximum possible. Or probably in some cases people may define some level of risk, and for that given a level of risk they want the maximum possible return. So that could also be one of the objectives which might be solved through this optimization solution. Sometimes there is a combination. I want my risk to be as much minimum as possible, and I define some level of expected return. So for this particular level of expected return, I want the risk to be as much minimum as possible. So like this, people can create different kinds of optimization problems and try to solve them accordingly using the mathematical or numerical kind of procedure.